what are coordinate systems, what are transformations, what is a tensor, and what are some of the properties of tensors, and also how to derive eigenvectors and eigendirections, I'm sorry, eigenvalues and eigenvectors to define a coordinate system. So today we want to talk about another aspect about tensors, which is more closer to how we will end up using this concept, which is let me throw out the word fields here. So if I talk about a field, uh, just tell me some of the thoughts or notions that come to your head. When I say a field of some quantity, what is that first you can think of? So some of the common usages like electric field, velocity field, temperature field, strain field. So when I say this, what what can you say to explain that terminology?
I think of a matrix.
Can you be a little louder, please? Or maybe I'm
Can
volume
you hear
level
me?
is.
Can you hear me?
Hold on. Wait, it's probably my end. Yep, yep,
Can you hear me? Okay.
yep.
I said I think of a matrix to model the field.
Okay, what do you understand by the word field itself?
Mm, a three-dimensional um, area of values.
Okay, so you're saying it's like a value that is assigned at each position or each point in space.
Yes.
Right. So when we say velocity field or temperature field, what we are referring to is what is the temperature at a given point, and that can vary from, vary across the space.
Mhm.
And that's pretty accurate. And usually we denote something as a field. We assign the value of some property like temperature or velocity to a set of coordinates. Like for example, if I write a velocity at a certain position, which I'll denote using x is being the position vector, and the velocity is the velocity at that position or at that point. I can write temperature at a certain point defined by the vector x, or I can write electric field, which is a vector at a certain point, or let's say strain, which is usually a tensor at a certain point x. Now, the important thing to keep in mind is at that certain point, there are a certain set of material atoms which exhibit this temperature. That is, you're not assigning temperature to a random point in vacuum. It is the temperature of a set of atoms that occupy the position x, or that occupy the point defined by position vector x. So any quantity that we have discussed so far, which could be a scalar, vector, or tensor, can be defined in continuous space. So I want to add a definition for what is a tensor field. A tensor field is a continuous function in space, in space. And for us, space usually means three-dimensional space. So we are going to denote it. I mean, okay, we'll come to denotion later. In space, which assigns a value or a tensor to each point. And the more important aspect is it is continuous. That is, if you are having a line, let's say there is a point defined as 1.0, and then there is a point assigned as 2.0. What you are implying by continuous is this. Oops, sorry. By continuous, what we mean is this line, which is like saying one-dimensional space, is infinitely divisible, meaning you can generate uh, 2 points between that, say 1.5, and you can keep dividing this further and further so that you keep ending up with a point at which your property is still mathematically defined. That makes sense. It's like saying every point, no matter how many precision, how many decimal points of precision you add to that position vector, it still has a value of that quantity assigned to it. Now, is that realistic? Like to say that space is infinitely divisible and you can keep adding or keep dividing it more and more until you reach some lower limit, what that lower limit might be. So if you take a block of metal and we are saying initially it has, let's say, a cubic shape before you apply any load and deform it. And every point in that block, you can assign a certain property value. It could be a tensor in general or a vector or a scalar. Let's say that tensor is like stress tensor or a load vector or a temperature scalar and so on. The idea of a tensor field is you can keep subdividing that. You can take any point and you can take any very close by adjacent point, and the function is still mathematically defined. That picture essentially assumes your block of metal is infinitely divisible. You can keep making smaller and smaller blocks and nothing would go bad. But that is not reality. What is reality? If you keep chopping further and further, dividing further and further, what happens?
You'd eventually get to one atom.
Which is not divisible, right? You can't fragment that further. And even before getting to that scale of one atom, if you are just reaching a scale where there are only few atoms, like 10 or 20 atoms, it's not enough for us to treat it to be a continuum. This is the discussion we had at the very first lecture, where we said, as long as our scales of interest are greater than atomic dimensions, we can use the ideas of continuum mechanics or continuous media. So this whole tensor field concept is an abstraction of reality, where we say that a tensor field is represented as a continuous function. So each of its components are continuous functions. But the word continuous function itself is with some restriction. It essentially means you are staying above the length scale that corresponds to atomic dimensions so that your math is still uh, logical. If you go too small in dimensions, you have to abandon the whole idea of continuum mechanics itself. So just keep that in mind. So we are going to say this tensor field, the components of the tensor are all continuous, well-behaved functions, and usually in mathematical terms that is called analytic functions. Analytic means it is continuous and differentiable. Analytic functions. So when we write, let's say, a tensor T, and we write Tij, Ei, Ej, if T is a tensor field, we assume Tij of X are analytic functions. So I'm going, yeah, that is T of X. T of X is a tensor field, and then Tij of X are analytic functions. And suppose we think of um, differentiation with respect to differentiation with respect to a spatial component. That is, if we just assume that we have some unspecified coordinate system defined by directions 1, 2, and 3, okay, with respect to this coordinate system, we say we take a point P, and let's say P has a coordinate X. So we can write X equal to Xi EI. We usually don't show this explicitly, not shown, but understood that it exists. The coordinate directions, the origin, we know that you need those to define a coordinate system, but we don't go about talking them each time. We just say that in an unspecified coordinate system, a point P has a position vector X, and X is given as Xi EI. And when we say differentiation with respect to a spatial component, I'm referring to Xi, where I could take values 1, 2, or 3 with respect to any of the three directions. Okay. So differentiation operation. So you can take, for example, a scalar which depends on position. And if we want to get the derivative of the scalar with respect to position, a scalar doesn't care about component, right? So it's just a single function. It's just a single function. So this is essentially partial S over partial Xi. And depending on how S depends on Xi, you will get some kind of algebraic function or a derivative to compute. And then if we think of a vector V can depend on position. So that is like writing Vi, which is a component which depends on position, times EI. So this statement means we always write V equals Vi EI. That is for a single vector. But when we write a vector field, what we are implying is each component is an analytic function of X, the position. Very simple concept, okay? Just extending what we know about individual tensors to that of a tensor field. And if I want to do the partial derivative of V, which is a function of X with respect to Xj, that is like writing partial over Xj, Vi, which is a function of X, times EI. So this is nothing but partial Vi over Xj times EI. So simple finding is derivative of a vector with respect to position, which in this case a scalar, yields a vector. We already did scalar. Scalar derivative with respect to another scalar gives you a scalar. And then you can do differentiation of a tensor with respect to position, which is like writing partial over partial xk, the tensor t, which is a function of position. This is like writing partial over partial xk Tij being a function of position multiplied by or written next to Ej, the dyad. So this gives you Tij, a function of position, over xk Ei Ej. I mean, I'm just in mostly repeating what is in the book with giving you some kind of nomenclature that we'll keep using to later simplify. So a symbol we want to introduce is partial s over partial xi. The book uses a shorthand that writes s and then comma I. We have partial vj, or I'm sorry, partial vi over partial xj, that is vi comma j. This comma I denotes denotes differentiation, or you can just write comma I denotes differentiation with respect to xi. And partial Tij with respect to xk may be written as Tij comma k. Just a shorthand notation. We'll use this moving forward. Okay. Any question? Are we okay so far? Am I going too fast? This okay? Are you able to follow? Do you want me to go back a few slides, see anything? No? Good? Okay. All right. So then when it comes to differential calculus, there are four. Oh, sorry. Okay. Thankfully, I didn't lose anything. Okay. So when it comes to differential calculus, there are four important operations: gradient, curl, divergence, and Laplacian. Now they all have some physical meaning, which I'll try to explain at least briefly. So let's start with gradient. Okay. So firstly, what is gradient? What is gradient? Before I say something, um, the word gradient itself holds a clue. Can you give me some thoughts on this? You know what is a derivative? dy over dx. What is a derivative? We know this from high school. Rate of change of the quantity y with respect to x. We've learned this so many times, right? So if you think of a function s, let's say it depends on x1, x2, and x3, like xyz, three coordinates. I'm calling it x1, x2, and x3. So when you talk about partial s over partial x1, or partial s over partial x2, or partial s over partial x3, What are we talking about here? What is this quantity represent? Partial S over partial x1.
Rate of change of function of S with respect to x1, x2, and x3.
So x1 and x2, x3 are directions. That is, it's like saying if I travel along x1 direction while I'm not moving along x2 and x3. So that is, if I write, say for example, this is x1 and this is x2, and I'm not going to draw x3 just for simplicity. So if I am here, if I just travel along x1 while staying at the same x2, partial S over partial x1 is also like saying holding x2 equal to constant. Okay. And if I do the other way, partial S over partial x2 holding x1 as constant, that is like traveling in this direction. What is the rate of change of this function along a particular direction, x1 or x2? That's what the meaning is. So if I write partial S over partial x1 multiplied by delta x1, what is this quantity? What is this rate of change? And what is this change in x1? If I multiply the rate of change along x1 multiplied by the change in x1, what do I end up with? Think of this like a simple problem when you encounter when you are, let's say, climbing a hill. You are somewhere in that let's say that landscape. If you travel along a certain direction, the altitude falls at a certain rate. Let's say, I'm sorry, yeah, let's say the altitude falls at the rate of if you travel uh, 1 mile along this direction, let's say the altitude drops by about 200 feet. And if you travel about 4 miles along that direction, what is the total drop in elevation? I'll say partial
800.
800. Partial S over partial x1 is 200 feet per mile. And if I travel 400, how much did I say? 4 miles. If I say travel 4 miles, then the total change in elevation will be 800 feet. Would you agree? It's a simple idea, right? And then if I travel 4 miles, I reach another point, and then if I travel along this direction, where let's say it drops by 300 feet per mile, and I travel 2 miles, I have 800, and then another 600. So that's a drop of 1,400 feet in total. So it's like saying this is the change in S due to change in x1. I can also do the same, partial S over partial x2 multiplied by delta x2. And then I can calculate what is the total change in S, which is partial S over partial x1 multiplied by delta x1 plus partial S over partial x2 multiplied by delta x2. And the same logic applies also if there is a third direction, delta x3. Okay, this is if I traveled along either 1 or 2 or 3, either along either of these three directions only. Only if I travel along 1, 2, or 3. This is the total change. Okay. Now, if I think of S, okay, the quantity, and instead of traveling along either 1, 2, or 3 directions, that is E1, E2, or E3 directions. What if we traveled along an arbitrary direction? We'll call it U, where you can write U is UI EI cap. I can define any direction, right, by its components. Instead of traveling either along the x-axis or y-axis or z-axis, what if I just travel in some random direction U? That's the question. So if I say partial s over partial x1 multiplied by, I'm saying I want to know what is the rate at which this quantity changes along U. That is, I'll state the question first before I state the answer. We would like to evaluate what is the rate of change of S along U. That is the question. Okay. So if I write partial S over partial x1 multiplied by, wait, yeah, multiplied by E1 plus partial S over partial x2 multiplied by E2 plus partial x over partial x3 multiplied by E3 dot U1 E1 plus U2 E2 plus U3 E3. I'm saying this quantity here, if I multiply together or do the dot product, I'm going to get partial S over x1 U1 plus partial S over x2 U2 plus partial S over x3 U3. Okay, so this quantity here has a specific meaning. This is the total change in S along the direction U. So previously, when we write partial S over partial x1 multiplied by delta x1, this is change along the x1 direction, or I would say E1 direction, along E1 direction. So this quantity here, partial S over partial xi EI, is called the gradient. It's called the gradient, and I'm adding this because it represents the rate of change along EI, which happens to be the basis vectors used in this case. That is, it quantifies the rate of change along the principal vectors or the basis directions. And when you dot product or do the and when you project it onto an arbitrary direction, you end up with what is called as ds over du, which is gradient of s dot u. This is the directional derivative, and this is the arbitrary direction, and this is the gradient. So this discussion you can also find in section 2.6.2 of the text. So this gradient is of special interest to us. You can write this as partial over partial xi times s of x. Or actually, let me write this a little bit clearly. Partial s over partial xi, where s is a function of x the vector. Okay. So one thing we can define or generalize here is this gradient operator is defined as partial over partial xi. Oops, or sorry, let me back up here. I left out one important thing, which is ei sorry. Yeah, good. Okay, so then here is this. I left out an important part of this gradient operator, which is the ei cap. That is, this gradient here is defined as this vector. So of course it comes with the derivative, the derivative operator along that direction multiplied by the basis vector along that direction. So a way to write the gradient operator is to write partial over partial xi of something times ei. So whatever that something is. Wait, I need to write this again. So gradient operator of something is partial over partial xi of that something multiplied by just scalar multiplied by ei. This is the gradient operator in index notation. So this something can be anything. This quantity that is on which this gradient is being operated on can be scalar, vector, or tensor. And whatever quantity that is, gradient operator will increase the rank +1. So if you operate the gradient on a scalar, you end up with a vector. If you operate it on a vector, you end up with a tensor, second order tensor. You operate it on a second order tensor, you end up with a third order tensor, and so on. It will increase the rank by 1 always. And you can easily see that. Suppose you operate the gradient on a vector. How do you convert this in index notation? That's your first task. This is partial over partial xi of something, that something being v ei. This is the gradient operator. And just to be consistent with the book, I'll write xj ej. And v itself, what is v? How do you write v in index notation, like a vector in index notation?
VIEI.
Vi ei cap, right? So vi ei cap, and then you operate this with respect to, sorry, you multiply that with ej. Now, in Cartesian coordinate systems, in Cartesian coordinate systems, ei, that is E1, E2, E3, do not depend on x1, x2, x3. That is, they are constant directions, let's say, which don't depend on where you are. That is, it's the same direction regardless of whether you're closer to the origin or farther from the origin. Then this derivative with respect to xj does not really operate on ei. Ei is a constant with respect to xj. So you can write this as partial vi over xj ei ej. This being a dyad and this being the tensor component. So what it shows is the gradient of a vector leads you to a second order tensor in the end. And you can, of course, do the extension to a tensor. So if you write gradient of a second order tensor, this is like writing partial over partial xk of the tensor with vector ek. And the tensor itself can be written as partial over partial xk tij ei ej of ek, that is multiplied by ek. So you have partial over partial of tij over xk ei ej ek, making this a triad and a third order tensor. Very simple concepts, right? You can also write this as tij comma k. Are we okay so far? Something's not clear? You want to ask something? You're able to follow? Is this? Hopefully the computer format is not too bad. Okay. So the time is 6:42 and our official time is until 6:55. But because we started at 6, I would like to go on until 7:30 if nobody has any objection. If you have a time conflict, please let me know right now. Okay, I mean, I'm going to record this, so if there are at least 3 or 4 people that will stay, looks like everybody will stay, we can do this. Okay. All right. So we saw gradient. The next operator we are going to see is divergence. I did write curl as the second, but I'll go to divergence and then come back. Okay, so divergence is an interesting operator. Divergence is defined as this: del dot something is what is del? That is partial over partial xi ei, and that is dotted with something. Clearly, that something can only be a tensor of rank greater than or equal to 1. It can be a vector or second order tensor, but it can't be a scalar. And usually divergence leads to the reduction of the rank by 1. So if you operate it on a vector, you get a scalar. On a tensor, you get a vector, and so on. So if we try this on divergence of V, this is partial over partial xi ei dot Vj. Now let me be consistent with the book. Xj ej dot Vi ei. So this is clearly partial Vi, partial Xj, and then I have Ej dot Ei, which I'll write delta Ij or delta Ji, however you want to call it. Which of course is like writing partial Vi over partial Xi. This is gradient of a vector, and then we can do gradient of a tensor, which is partial over partial xk ek. See, this practice I want you to get into. That is, if you write an operator, which as we will do later for doing problems, you start with what is a gradient dot what is the second order tensor Tij ei ej. So this is Tij comma k multiplied by delta ki times ej. That is, I skipped one step here. This is nothing but ek dot ei. So this is, I have to set I equal to k. So this is Tij comma I ej. So divergence of a tensor gets you a vector. I told you that the rank always goes down by 1, right? So rank went from 2 to 1 in this case. So here's a couple of identities that the book suggests that we try. So divergence of a vector is equal to the trace of the gradient of the vector. Can we prove this? You can do it two ways. You can do brute force, substitute everything and show that left side equal to right side, or you can use index notation, start with the right side and show that it is actually same as the left side through algebraic manipulation. Let's try the second option. Okay. What is trace? Trace of a tensor. So you do know that gradient of a vector will give you a tensor. So that part is already known, and you can start like this. What is gradient of a vector or gradient of V? That is partial over xj V ej. This is practice I'm giving you to do this thing repeatedly. So this is partial over xj Vi, Ei, Ej. Vi, Xj, Ei, Ej. That's the tensor whose trace you want to compute. And how do you compute trace of a tensor? What is trace? It is the sum of the
diagonal elements.
diagonal elements. That is, if you have, let's say, a trace of a tensor A, it is nothing but AII. That is trace. So that is like saying Aij multiplied by delta ij. So I have trace of delta V, which is like saying partial Vi over partial Xj multiplied by delta ij. So this is partial Vi over partial Xi. Right? And this is nothing but del dot V. You know this. If you directly do the gradient and dot product that with your component of the vector, you will end up with the exact same expression, proving that this left side equal to right side. So it's a very simple identity to prove. Like, do you agree with this? Am I just saying something you can't agree with, or is it understandable? Is it okay? Thank you. Mark, is it okay? Yeah. NC, Morteza, is it fine?
Yeah, it's fine.
Okay. All right. So another identity to prove is divergence of a tensor, which will give you a vector dot A, which is an arbitrary vector, is equal to divergence of the transpose of the tensor multiplied by A. No, dot product here. So this is the identity we are asked to prove, and we'll start with maybe the left side and use index notation first. What is divergence of a tensor? That is partial over partial xk, Tij, Ei, Ej, partial over partial xk, Ek dot Tij, Ei, Ej. Gradient operator dot tensor. So this is partial over partial of Tij over xk delta ki ej or Tij comma I ej. Tij comma I ej. And what is A or what is this quantity? Divergence of the tensor dot A. So we'll write this is Tij comma I ej dot. We can use any dummy index we want. We can use K or L because I have not used L so far. I'll write this is AL, EL. So I have to do EJ dot EL. So this is Tij comma I multiplied by AL multiplied by delta JL. So this is Tij comma I AJ, which is shorthand for partial Tij with respect to Xi multiplied by Aj. And now we have to also show the right side will also reduce to the same expression, which will prove that they are both the same, right? So what's the right side? Right hand side is divergence of T dot A, which is, I'll leave divergence alone for this for the time being. This is Tij EI dot AK EK, or divergence of Tij AK EI delta JK, which is divergence of divergence of this keeps happening. I'm sorry about that. Yeah. So this is Tij AK EI multiplied by delta JK, or divergence of Tij AJ EI. Okay. And then divergence is, now I can write this as XL EL dot Tij AJ EJ. So it's 6:55. If anybody has a big objection to continuing, please speak up. Otherwise, I assume we are all okay and safe and to continue until 7:30 or 7:25. Good. Okay. If you want to skip out, feel free. I am recording this. So this is uh, this is going to be partial Tij XL EL multiplied. I'm sorry. Sorry. This is partial with respect to XL Tij AJ multiplied by EL dot EJ. So this is partial with respect to XJ Tij AJ. Did we do everything right? Want to make sure. Okay. So here we are. Oh, wait. This is supposed to be divergence of T transpose. So everything that I did is actually wrong. We have to redo this. I left out the transpose. So before I do that, what would change if we have to work with T transpose instead of T? How do you write T transpose in index form? I'm going to erase all this. Yeah, tell me.
Tij EJ cap Pi cap.
So are you saying this? If T is expressed as Tij EIEJ, then the transpose of T is Tji EIEJ. Are you saying this? Okay. So if we want the transpose of T dotted with A, that would be Tji EIEJ dot, I'll do AK EK. Okay. So I'm going to delete these two slides because they were wrong. All right. Okay, so this is going to be T J I A K E I delta J K, or this is T J I A J E I. And you want the divergence of this. Okay, you want the divergence of this quantity. So divergence of T transpose dot A is partial over partial xk ek dot T transpose dot A. Partial over partial xk ek dot, what is the thing that we just worked out? That is, this is T J I A J E I. Yep. So this would be partial over partial xk Tji Aj delta ki, or this is partial over partial xi Tji Aj. How is this same as this expression? Divergence of T dot A. How are these two the same? I'm going to collect them and write here. Okay, so add one more slide. I'm going to write divergence of T dot A is equal to partial over partial xi of Tij multiplied by Aj, and divergence of T transpose dot A is partial over partial xi of Tji Aj. How are these two equal? We have to show they are equal. Any thoughts? You can say something. You don't have to be correct all the time. Okay. So I would first try to work on the right side and try to see if we can get it any closer to the left side, and while also remembering what we have done about dummy indices. Whenever you see patterns that repeat themselves, you have to try to see if you can combine them. Okay, so here goes. This is partial tji xi multiplied by aj plus tji partial aj over partial xi. What do we do next? Okay, since I'm not getting any response, so tomorrow's lecture we are hoping to dedicate to discussing the homework. So these are some of the things you would encounter when you do the homework, and I want some response from you tomorrow. Okay, when we do the lecture in the afternoon at 2:30. Tomorrow's is mostly discussing the homework and these sort of derivations, which I'll come with some notes, and we are going to give you hints to complete the homework. So I want some response tomorrow, please. Okay. Today I have some time. I want to get through some of the topics. So we talked about gradient. We talked about divergence. Let's get back to curl. Okay. The curl operator is defined as gradient cross something, where that something is usually a tensor of rank greater than or equal to 1. So it can be a vector or tensor or a higher order tensor. Okay. So when we write gradient, we usually know this stands for partial over partial xi ei. And when you're doing the gradient cross something, you have to think of how do you do A cross B. Recall what is A cross B in determinant notation or matrix notation. This is epsilon ijk ai bj ek. Right? So you can also write this as E1, E2, E3, A1, A2, A3, B1, B2, B3. This is what we know about the cross product. So when we do gradient or sorry, curl of a vector, what we are writing here is partial over partial xj ej cross, we'll call this vi ei. So this is partial vi over partial xj yeah multiplied by ej cross ei, or just to keep the nomenclature cyclic, we write partial vi over partial xj ei cross ej, which is usually ek. So we write minus vi xj ek multiplied by the permutation symbol ijk. So I would write del cross v is minus epsilon ijk vi xj. Is that what I wrote? Yep, vi xj times EK. Curl operator. Curl of a vector. Unlike the other two, the rank doesn't change. It stays the same. You get the curl of a vector also to be a vector. So, excuse me. I mean, if you go through section 2.6.2, try proving all the identities given in there, because either we'll use them or they themselves could be like an exam problem, like the one we tried a few minutes back and said we'll continue tomorrow. So if I take another identity given here, it goes as gradient of V minus gradient of V transpose dot A is equal to the curl of V cross A. Before you do anything, what kind of a quantity is the right side? Is it a tensor, second order tensor, or a vector? What kind of a quantity? Curl of a vector is a vector.
The vector.
Yeah. So you get a vector cross another vector, which is again a vector. So this is a tensor dot a vector gets you a vector. Of course, they should agree because they are the left and right side. They should represent the same thing. So gradient, or sorry, curl of V is minus epsilon ijk partial Vi over partial xj ek. So this is something you should kind of remember, just like we remember Vi is Vi Ei. Wherever you see the curl of a vector, you can directly start from here and then start doing the algebra. These two quantities, the curl of the vector as well as the velocity gradient, will be frequently encountered in fluid dynamics. One is called vorticity, the other is called velocity gradient. Okay, we'll see them quite a bit when we talk about fluid mechanics. You may ask then, what do we then encounter in solid mechanics? At least physically, you know that solid mechanics is more about strain than about strain rate. So just a small digression here. So when we talk about fluid dynamics, we talk about gradient of velocity, the vorticity gradient, I mean the delta cross V. And when we talk about solids, the more interesting quantity is the positions or the change in positions. So we talk about delta X, which will later be called as the deformation tensor. And then we'll have various measures of the deformation tensor contains info about the strains and a lot of the next unit will be dedicated to understanding the properties of F, the deformation tensor. That's the whole thing about kinematics. Okay. And the last thing I want to talk for today is Laplacian which is del dot the gradient of something. So this is usually written as del squared of something, and this something can be scalar, vector, or tensor. So usually del squared of a scalar is also a scalar because this operator here, del squared, is a scalar operator. If you do the del dot del, you will end up with second derivative with respect to xi. Sorry. Del squared is basically second derivative with respect to x1 squared, second derivative with respect to x2 squared, plus second derivative with respect to x3 squared, operated on something. So this is until everything that I talked today is section 2.6.1 and 2.6.2. That is the discussion on Cartesian operators, that is these differential operators in Cartesian coordinates. The same operators, that is gradient, curl, divergence, Laplacian, in curvilinear like cylindrical or polar coordinates is also important. And I don't want to rush this in the last 10 minutes. So my original plan is that we will do homework problems tomorrow and then start the next unit on Thursday, which I'm now trying to, maybe I'll change it to finishing this unit tomorrow, discussing the section 2.6.3 and 2.6.4. We'll discuss those tomorrow and then do the homework discussion on Thursday, so that by end of this week we'll wrap it up, and your homework will be due on Tuesday. That's the plan. Any questions about the planning? Is it clear? Okay.
Yes.
So thank you. So homework 1 is still due next Tuesday at the start of the lecture. You can do paper copy or PDF copy. Just email it to me. Either is fine. And that programming exercise, I have already entered that in the homework 1 document. You just have to follow the instructions, and that will be due the following Tuesday, which is March 4th. Okay. And March 6th, I plan to hold the first exam just on unit 1, that is just on tensors. This entire unit will be the only topic covered in that exam. Whatever we start next week on kinematics related to deformation gradient, it won't be on the exam. We'll do it for the second exam. Okay. So entire homework 1 content, which is chapter 2 in the textbook, is what is going to be on the exam planned on March the 6th. Is that okay? Any questions? Something not clear? Okay. So to wrap up, homework 1 due Tuesday, the programming assignment due the following Tuesday, March 4th, and exam 1 is on March 6th, covering only chapter 2 from the textbook. And maybe next lecture or tomorrow, I'll also tell about how many problems will come up in the exam and which sections those problems will cover. So if, for example, it might be 3 problems covering 3 sections, I'll exactly tell what is the structure of each of those 3 problems so that you can start your preparation. Okay.
So I have a question.
Yeah.
So can we change the exam time, because I have another exam exactly March 6th?
The following week is spring break, so I don't know where I can push the exam.
Okay.
Like, I mean, you have another exam on the same day in another course, I assume.
Yeah, exactly.
I am sorry, but this mean like I can't push it the following week because it's spring break, and You have like 2 or 3 weeks notice, so hopefully you'll be able to plan for it.
Okay, thank you.
Yeah. Okay. Thank you. So tomorrow and Thursday we'll try to wrap up this unit. Okay. All right. I'll post these slides and recording later today. Thank you.
All right. Thank you.
Thank you. Yeah. See, tomorrow's lecture is also on Teams. Okay.